So far, we've looked at models where there has been a lot of homogeneity. All the households are the same, and also all the firms are the same. In fact, with constant returns to scale, we've been able to avoid thinking even about how many firms there are, for example. So that leaves two questions. First, is it possible for households to be heterogeneous in this environment? The second is it possible for the firms to be heterogeneous in this environment? And firm heterogeneity is what we're going to look at today because it's simpler and it's going to introduce some basic concepts that are going to be useful for talking about heterogeneity in general. So let's take a look. Now let's go back to our simple growth model where we had two state variables. One was the capital stock, K, and the other one was a random variable ZT, which was productivity. Now, if we wanted to have heterogeneity in this model, we would have to decide exactly in what way agents are heterogeneous. And there are two possibilities here. One is that you could have agents with different amounts of capital. The other is that you could have firms with different productivities. It turns out that the second possibility is a lot easier to deal with than the first, the reason being that to get heterogeneity of capital in the first case, you'll probably need some kind of incomplete markets, incomplete insurance, for example, or limited asset markets, only certain kinds of assets can be traded. And that's a whole complicated topic. So let's suppose that we have heterogeneous productivity. And to make things simpler, we'll also assume we have no capital at all. That's going to be able to help us focus on exactly what are the mathematical objects we need to worry about when we have heterogeneity. In particular, here's a question. What is the state variable in an economy like this one where there's no capital, but you have a lot of different firms and they have different productivities. And of course, these productivities may change over time. The answer is that it is going to be the distribution of values of Z across firms. If there are a finite number of possible values of productivity, that distribution is going to be a vector. If there is a continuum of possible values, then that distribution is going to be a function. And if we've set up our problem, which we will actually, in such a manner that the number of firms or the mass of firms is not exactly one, then it'll be more correct to say that what we'll have is not a distribution, but rather a measure of productivity across firms. And you could think of a measure as just being like a distribution, except that again, it doesn't have to add up to one. It could add up to anything depending on how many firms there are. So, for example, suppose that productivity follows a Markov process so that there is some probability distribution F, so that you have productivity of Z plus 1 at a particular firm follows some distribution F which depends on the value that Z had yesterday. In addition, there is a mass epsilon t of new firms born each period. And just for simplicity, let's say that all firms die each period with probability lambda. Well, with this information, we can already say something about how many firms there would be if there are MT firms. Then we're going to have that MT plus 1 is going to be equal to whichever firms from the past did not expire plus epsilon t. No particular reason why MT plus 1 or MT should equal 1. In fact, suppose, moreover, that there is a steady state value of epsilon. Suppose there's some way in which we can get a stationary equilibrium in this environment. We'll get to that later. Then what is M going to be in the long run? We just remove the time subscripts there. Well, very clearly, we're going to have that M cancels with M here. So you end up with lambda M on this side. And of course, that just means that in the long run, this is going to be the value of M. You can also easily verify that because this is between 0 and 1, you'll converge monotonically to this, regardless of what MT you started with. And again, there's absolutely no reason why this should equal 1. And that means that if we were tracking the full measure of productivity across firms, the total mass of that is going to converge to this. To be more precise, suppose that mu t is the measure of productivity across firms. This, of course, is the state variable of this economy. What we're going to have is that the integral of this over all values of productivity is going to equal MT. And since we know that that converges to something, that's going to converge to epsilon over lambda. Of course, we would like to characterize this full measure more than just knowing what its overall mass converges to. And for that, for simplicity, let's suppose that ZT is drawn from a finite number of possible values, Z1, Z2, Zn. Well then, this measure is very simple. It's just a probability that if you randomly pick a firm in this economy, you're going to find that it equals a particular value of these, times, of course, whatever is the total mass of firms on that date. So let's write that. Ut is just the number of firms with productivity T equals Zi. And how is that going to evolve? Well, let's take mu of one of these values. How can you end up with mu of zi? Well, one possibility is that you had that value before. Of course, you would have to have survived, so this is 1 minus lambda in front. Or alternatively, you could have had one of the other values survived and made it to zi. Incidentally, we also have to multiply here by the probability of being at zi, given that you were already at zi. For the others, again, you had to survive. You had to have some mu of zj, and then you're going to zi, given that yesterday you had zj, and of course this we want to add over all the possible values that don't equal I. Finally, one element of this model we had yet to discuss is that when there is a new firm, there's a massive new firms here. Those new firms, of course, also need to have some productivity, and that needs to be drawn from some distribution. So let's say productivity new firms is drawn from some distribution psi. So then here, another way in which you could end up with zi is because you were born, this is the number of firms born, and you just happen to be born with that productivity value. And of course, this can be simplified because this is dealing with the possibility of going from zi to zi. This is dealing with all the other ones. You can just smoosh this all together and see that this is adding up over all the possible values of j, which goes from, of course, 1 to n. There. So that's the transition function for the case where we have a finite number of z's. So this is a transition function for the measure. Now, if we had a continuous measure, in other words, z is drawn from a continuum of possible values, then things would be different. In that case, we can't say anything about the probability of any particular value or the measure of any particular value of z because it's going to be 0 because it's continuous. So instead, what we have to do is the following. First, we'll start by showing an analogous way of thinking about the measure in the case of finite values of z by doing the following. Note that suppose we wanted not to figure out the probability of a particular value of z, but suppose instead we wanted to figure out the probability of being in some particular subset of values. The subsets z. So now I want to figure out the probability of that. And of course, that's just the sum of the probability of each of the individual ones. And of course, that would be exactly the same here. I would just be adding here, it would be a double sum over the zi's that are in my big set Z. And the same here, mind you. Now you could say, well, this equation is of course equivalent to this one, ultimately. What happens is that while this one doesn't have a counterpart for the continuous case, this one does. And if you imagine that mu is now a continuous measure over a continuous set of z's, and now let's call z some measurable subset of the space, the continuous space from which productivity is drawn. Let Z now be any measurable subset of the space from which productivity is drawn. Here, instead of being a sum, this will be an integral. So again, this now is meaningful, where the mu of any particular value is 0. But now we're integrating over several values, over an area value, so to speak. There is a meaningful measure. This would now be just integrating over all possible values zj. And here again, we also have to integrate, and we would get something that applies for the continuous case. Great. So again, I think everything is clearer in the finite case, and in most cases, if you're actually going to simulate anything, you will want to look at the finite case, at least when you get down to actually programming. So let's go back to the finite case. In the finite case, we have this. And just as if we think about the total measure overall, it's going to converge to something. You can imagine this is also going to converge to something. So let's remove the time subscripts and consider a hypothetical steady state. So epsilon is constant. You can see that this is also going to converge to something, and there's several ways to see that. One is if you think about our Bellman equation from before, maybe something analogous is going to work here, and that's true. That intuition is what's going to get us to be able to find a steady state here. You imagine that this is a value function. There's no maximization here, but here is something that looks like discounting. And so it's provable that indeed you can use the Bellman operator in some context to show that there must be a steady state here. But in the finite case, of course, it's easier. And to see that, why don't we realize that just like Zi, or rather Z is a vector, right? There's a finite possible number of values of Z. That means that mu itself is a vector. So rather than writing mu of Z, why don't we just stack mu of Z1, mu of Z2, mu of Z3, and so on top of each other? Just call that mu. This is equal to 1 minus lambda what? Well, this is a vector mu. This is a matrix, right? It's a matrix that tells you, give me one Zi, let's say, and I will tell you the probability that you get there out of some zj. So that's a matrix. And that matrix is times this vector from yesterday. So if we didn't want to suppress the time subscripts, we could just have done this actually in general. And then this is epsilon times the vector of probabilities psi. Again, if this were not the steady state, we could just do this and use that as a vector representation of our transition function. Of course, you have to make sure that everything is ordered properly here. So if mu t is a vertical vector, then you need the rows of f to be the probability of going from any particular j to the corresponding I here. But let's assume that we've done that. Then, if we're thinking about a steady state, so this has reached some constant, we can suppress the time subscripts and see that in the finite case, it's actually pretty easy to figure out what's the steady state, because notice that mu is the same as the identity matrix times u. Subtract this expression from both sides. And factor out mu. So the steady state mu is going to be, well, just multiply both sides of this by the inverse. And we're done. That's how we're going to find the steady state value of mu in the finite case. So now we've talked in some length about what is going to be the state variable in an economy like this and how we can characterize a steady state if there is one. The next thing we're going to want to look at is, of course, the behavior of the agents in this economy. So let's start with technology. So suppose that each firm has the following production function. The production function is going to be that the output of a particular firm is its productivity, which again varies across firms, times nt to some power. Great. Next, we want to write down the value function for a firm. And a firm in this environment maximizes, let's call its value function v. And v depends on two things we have to be careful about. One is the state variable at the firm level itself, which is going to be its productivity. But there's another state variable here. What is that? It's mu. And why does mu matter? Mu matters because in equilibrium, prices are going to be a function of that. Minus the wage times labor. So it's maximizing its profits. And again, some discounting, or I guess more generally, there's some interest rates that it uses. Then tomorrow we have zt plus 1, mu t plus 1, and of course an expectation. And that's it. That's their life. Notice that N is not a dynamic decision, at least not here, so we can actually solve out that part of the firm's life very easily. This, of course, has the following first order condition. And so we very quickly get to the idea that in equilibrium, N is just going to be this function. There. For all firms, which of course we can plug back in here and get a simpler expression. Notice that we can show that both of these things actually share a lot of factors. So let me put brackets around it. For example, you multiply z here, you'll realize that it's actually a function of zt to the 1 over 1 minus alpha. So we can take that out. If you look at the wage, you'll see that both of these are functions of this. So the wage goes out. And we're left with this very simple expression. Now, if you suppose that we're actually in a steady state, then all of this is going to look much simpler, because W is going to be a constant. And if we suppose that there's no growth and no population growth for simplicity, this is just going to be the discount factor of the agents. We haven't seen their preferences yet, but we'll get to that soon. And that's it. This is going to be our value function. And now, just like we were able to solve for this over here, this measure using vector methods, you can do the same here if you tell me what W is, right? If someone were kind enough to tell me what the equilibrium wage is in the steady state, we could compute this easily for the finite case, because V is a vector. It depends on mu star, but of course the way it depends on mu star is through W. Once we know W, once we know what W is, that's all we need to know, leaving V as just a vector. Mu star is what I'm using to call the steady state value of this. So we could draw this, we could represent this in vector form, say V is that vector. It's equal to something times a vector here. Well, it's equal to this, which is also a vector if we're stacking it for values of z one on top of the other. Let's just call it little v, plus beta. And what's the expected value here? Well, it's just f. Right? That's what we're using to get our expected values from. We're adding, given some value of z, this then adds up over the probabilities of each of the possible future z's. If we stack those things, we have beta f times v. And again, we can subtract this from both sides. And then this is just the identity matrix times this all inversed. So we could easily compute that if we knew what W was. And we can actually figure out what W is quite easily here. There's one thing missing here from our model setup, other than the utility function, and that is that we know that each period epsilon t new firms are created. We didn't say how. Now we're going to say how. At cost, let's think of a good name for the cost, kappa. So at cost kappa, you can create a new firm, or the households can create a new firm. Kappa is in this case determined in units of the final good, which all of these firms make, producing them and selling in a competitive market, or again, you may be solving the planner's problem. Either way is fine. And so, what does that mean? This means that in equilibrium, it must be that if there is entry, the value of creating a new firm must equal this cost. Now, suppose that it takes one period to set up a firm. This is an assumption that's embedded in something we discussed earlier, which was that in the measure, when a new firm is created, its new productivity does not appear until the following period. Then this implies that this cost kappa must be equal to the discounted, in the continuous case, integral of V over possible values of tomorrow's productivity given the future measure based on the measure of incoming productivity values, psi. In the finite case, what we get is, of course, a summation rather than an integral over all values zj that productivity might take, where psi is just the weights that they would get. And in the case of the steady state, we're going to have the steady state measure here. Great. Next up, we need to think about our households. To characterize our households, we need to start from the utility function. The instantaneous utility function depends on consumption and leisure. But actually, what we're going to do is go with what we had before in our recent example, where labor is indivisible. So then we can express this utility function as linear, where theta is the marginal disutility of labor. Let W be the value function of the household. It's going to be a function of mu, and it will be the max of this plus W tomorrow subject to, well, what are the possible things that this household could spend money on? One is consumption. Another is new firms. And this, of course, must be less than or equal to the wage times the amount of labor expended. And there is one more possible source of income. Recall earlier that there are decreasing returns to scale in production at the firm level. That means that there could be profits. From all the firms the household owns. Now, as we have been discussing, it is possible that the measure here could change over time, and so there could be aggregate uncertainty, there could be transition dynamics, and so on. But for now, just to make things clearer, let's focus on a stationary equilibrium, where we have a value function, an employment rule for the firms, which we discussed earlier, a measure mu star that is constant, consumption, choices of labor at the household level, a wage, and a value of epsilon such that a variety of conditions are satisfied. First, firms and households are optimizing given W, which is the only price in this economy in a stationary situation. Two, the free entry condition is satisfied in all dates. Three, mu star is a fixed point of the transition function for the labor market clears. What we're going to do now is continue to prove that this exists. First, it should be straightforward to show that given this value function in a stationary equilibrium, we will have that consumption satisfies a condition that C equals W over theta. And that means that this equation here is going to simplify. Next, notice that by definition, the profits earned by any firms here are going to equal the following. First, the profits are defined as just whatever value of productivity a particular firm has times whatever labor it chooses minus the wage. And just to be careful, let's index this by I. So this is the labor chosen by a firm with productivity I, which we derived earlier. So these are the profits of a particular firm. Now we have to add over all the firms with different ZIs and multiply, of course, by the measure of firms that have that particular value, ZI. So let's plug this into the above. And this is what we get. This is going to simplify. Why? Because think about what is going to be the labor market clearing condition. This is total labor supplied. This, if you add over all the firms and weight them appropriately, is going to give us the total labor demand. Now in equilibrium, labor demand and labor supply have to equal each other. And what that means is that this is the total wage bill that households earn, and the sum over all ZIs weighted by the measure of the wage bill of each firm is going to be total labor demand in dollar terms. And so these two things will cancel out in equilibrium. Finally, because of local unsatiation, we know this has to be equal. No resources will be wasted. And so we now have a simpler equation. Finally, I'm not going to write the expression, but remember that labor here depends on I. There is an optimal amount of labor that any firm with a particular value of productivity, ZI, is going to select. So this is ultimately a function of ZI. Finally, let's remember that we have a function for our steady state measure, which is that mu star is equal to the identity matrix minus 1 minus lambda f inversed times epsilon psi. Notice that this function is completely linear in epsilon. So now let's define a new function. We're going to call it mu star of zi given epsilon. So give me a value of epsilon, I'll give you a mu star. And now let's examine again this budget constraint. And notice that we have, in a steady state, this expression. Let's now replace this with this function. And notice that since this is linear in epsilon, this here is the same as if we assume that epsilon was 1, the whole thing times epsilon. And notice that if we assume epsilon is 1, we know exactly what this is, just as if we assumed epsilon was any other particular value. So that means we can take this and take out epsilon. So this is a known value. This is known. This is known because we figured out what W was given the free entry condition. This is a constant, given that we know that W. And therefore, this is a constant, this is a constant. Both are positive, and there is only one value of epsilon that is going to satisfy this equation. Of course, this would fail if kappa is so large that this whole expression is negative. But of course, those are not empirically relevant values. So for empirically relevant values, there should be one epsilon that satisfies this equation. And that means that we have solved this model. Good job.